Bromination of an alkene is actually a very fundamental reaction in organic chemistry. This is a type of reaction that's very dependent on the solvent that you use. For example, in this first case, if you use a non-nucleophilic solvent, such as dichloromethane or so, you end up with the bromine adding two bromines across the carbon-carbon double bond, and they add in an anti-fashion. Now, with most anti-additions, you go through a three-membered ring intermediate. The way the mechanism works. So you have electrons from the pi bond go up to the bromine. A lone pair from the bromine goes to meet the hole that's being vacated by those electrons. You also end up kicking this bromide off. The net result is you get the bromonium ion. Now this species is not particularly very stable. And the bromide ion comes back and does an SN2 reaction, where it opens up the three-membered ring. Since it's an SN2 reaction, you see inversion on the alpha carbon that is attacked. And you get this product, as well as it's an enantiomer if the bromide attacks the other direction. Now, you get two bromines across the double bond when you use a non-nucleophilic solvent like dichloromethane or chloroform or carbon tetrachloride. Now, if you do this reaction in water, you get a different product, where you get addition of a bromide and an OH group. Again, they add anti to each other, but the thing is the OH will go on the more substituted side. So it's an anti-addition of an OH and a Br, but the regiochemistry is Markovnikov-like, where the more electronegative element goes on the more substituted carbon. The mechanism starts out just the same. Where the pi bond heads up to the bromine, one of the bromines gets kicked off, and the electrons go back down to fill the space. And you form the bromonium once again. Now, this bromonium is actually reactive enough for water to act as an SN2 nucleophile. And water is more prevalent in the solution than bromide is, and so water can actually outcompete the bromide and attack. And it's going to attack on the more substituted side. You can show this step as reversible or irreversible. Sometimes they are, sometimes they aren't, so we're not going to hold you to it. Final step to get the product is water comes, takes the proton off, and you get your final product. Of course, since this product is chiral and this product is achiral, the starting material is achiral, you get a racemic mixture. If you use an alcohol in its place, instead of getting what's referred to as a halohydrin, what you end up getting is a haloether. To make this ether, where the R group is a methyl group, the solvent that you use is methanol. Again, the reaction is pretty much the same reaction, where the first step is formation of the bromonium ion, and now instead of water attacking, you have another nucleophilic solvent, methanol, that's present, and that attacks. Opens the ring up, you still get attack on the more substituted carbon, and the side that you attack on gets inverted because it's an SN2 reaction. And then methanol comes to deprotonate the product to give you the final product. Again, molecules start off with is achiral. Molecules you add to it are also achiral. The product is chiral. Since you're going from achiral to chiral, you get a racemic mixture. Okay. Now, you can do the exact same reactions you do with bromine, you can also do with chlorine. The only difference, at least at the 343 level, is that you substitute the bromines for chlorines. Still anti-addition. When you mix it with water, you get halohydrins. When you mix it with alcohols, you get haloethers.